Good afternoon and welcome to the 28th annual exhibit of Hydrogen and Fuel Cells Europe. We've been here for a long time discussing the technology, where it is and where it's going. I'm going to be talking to Arthur Gosling, who's Director of Strategic Sales and Sustainability at Emerson, and we'll be discussing project and operational certainty for hydrogen products. Welcome, Arthur.
Thank you, Brian, and good morning, everyone. We're very happy to be here today. We've been at Hanover for many years in the past, in different halls. This year is the first time we're here at the Hydrogen Hall, so we're very excited to meet all of you and showcase Emerson's automation solutions for hydrogen projects going to large scale.
And Emerson, you mentioned that you've been here in other areas of the Messe, the trade fair, for quite some time. First question, Emerson is a large and long-standing company. Tell us a bit about Emerson.
Sure, pleasure. So Emerson's a public traded company on the New York Stock Exchange. We're based in St. Louis, Missouri, and we're a global technology and engineering company. We have around 86,000 employees worldwide and about 200 manufacturing sites. We have a pretty deep value creation in terms of from products to data solutions. It's designed and manufactured all around the world by our teams. And that leads us to have 21,000 active patents at the moment. And we've been around since 1890 in different industries, from process to discrete industries. And so now we're very excited about the future, the potential that decarbonization and sustainability hold for our company and for our stakeholders.
So you're either the oldest or the second oldest company in this whole trade fair here in Hall 16. Just wanted to add that. It's kind of historic. Over this time, we've had a change in focus on energy towards renewables. What changes is taking place at Emerson as we face this dilemma of climate change and renewable energy?
Thanks for the question. That's a good question. So at Emerson, we've recognized the need and the shift and the refocus of the energy markets and the carbonization outlook. So we've now taken some pretty deep changes and appointed for the first time a Chief Sustainability Officer, who's Mike Train. He's been in the company for 30 years, Executive Vice President, acting now as Chief Sustainability Officer with a global team driving change throughout the organization. And we actually look at it in terms of three aspects. We look at it in terms of greening of, by, and with Emerson. And of course, we need to look internally first. So greening of refers to our scope 1 to 3 emissions, our own manufacturing footprint, the way we do business, and that's something that we take care of. We set aggressive targets there. The greening with is how we work with institutions, regulatory bodies, and policymakers to shape that future that we want to build together. So here, some examples are that we work with locally represented organizations like the NEMUR, the ZVEI, also VDMA, Power to X for Applications Group. So kind of to shape the technology that we need to make this transition successful together. And then the greening by is what we're exhibiting here today, is how our product portfolio with existing products or with newly developed products has changed to serve this emerging applications, these new markets, such as electrolysis or hydrogen mobility. So due to our history, we've dealt with hydrogen for a very long time, actually, from industrial scale production, steam methane reforming production. So hydrogen measurement, hydrogen control in and of itself is not a new demand for us in a way. Like some of the products have already have a pretty good fit around that in terms of safety and performance. But the new applications in electrolysis sometimes require changes in line sizes, changes in pressure ratings, and that's something that we've been evolving, adapting our portfolio towards to also be able to serve these customers.
So largely your expertise in gases has allowed you to actually move into the hydrogen generation, hydrogen usage field relatively easy.
Yeah. Even if you look at other alkaline type of technologies in the chlor-alkaline space, which has been used to produce chlorine for industry for a very long time, it's also an alkaline electrolyzer process. Emerson's been heavily involved there in the past, we still are, and by volume, half of the European chlorine production is run on our control systems, on our Delta V control system, so we have had pretty good experience in that space.
Okay. Our topic for today is industrial processes and plant automation. It's a big topic. How do you differentiate or discuss industrial processes and plant automation? How do you approach those topics?
Yeah, as Emerson, we work with technology licensors, with EPCs, OEMs, and the end users, depending on who's actually speccing the project. But we look at it, of course, as the title of the presentation also says, in two phases: in the project development phase, the capital expenditure phase, the time that we design and then execute, build the project, or the operational phase of the project, where actually the plant is running, and now we're talking about maintenance, now we're talking about asset health, now we're talking about other types of requirements that we look at. And so we have dedicated programs around project certainty for that project developing and execution phase, and then operational certainty for when the plant is running, when we're talking about maintenance and performance of whatever has been built. Yeah.
So what role in that whole equation does the digital side play? The potential for using data from the creation through to the monitoring and operation.
So there's an unequivocal trend towards automation and digitalization to be able to see more of what your asset is doing, and that starts way back from our history in terms of the level 1 field instruments, field devices that are valves, regulators, control equipment, measurement equipment that in the past may have been manually operated is now automatically operated. In the past may have communicated analogously when a 0 to 10 or 4 to 20 milliamp. Now we have more mature industrial digital protocols embedded into these field devices that then allow us on the control system side to be more flexible in the way we design the system architecture, be more effective, more modular. So we're also aligned with NOAA and MTP protocols to be able to tie into that whole digitalization trend from the field devices to the control layer. And that then, if that is a project that has been born digital and has been including all of these technologies, we then have the ability to feed that up to a global layer 3, layer 4 enterprise solution for our customers to have a visibility on their global install base and to see what their assets are doing.
Some of this involves, you mentioned it once there, maintenance. When I look at the meaning of that word in English, I always think of apartment buildings, and when you walk in, you're going to find a sign somewhere, maintenance, and a telephone number. And that basically is a direct reference to a guy with a hat on and overalls and boots. There's various ways of doing maintenance. One of the interesting things is how does maintenance prevent the necessity for maintenance? How does this all fit into the equation of maintenance, the modernization of maintenance through digital facilitation?
Yeah, that's a deep question. Essentially, moving from an interval-based, expected timeline maintenance that requires a person to walk through assets and take notes, perhaps even on paper, you know, how we used to do it in the past. Shifting from that to having digitally enabled field devices that give you continuous feedback on how their status is, maybe not only the current status, but also captured in a histogram, how have they performed over time. We can then assess and analyze the trends of the asset and identify problems before they occur, then leading to need-based maintenance versus interval-based maintenance. And that's something that in electrolyzer projects which may be built near the renewables offshore or deep in the desert next to solar projects, where you don't necessarily want to pay someone to go there routinely to then detect problems that may or may not have occurred. But if we then start from a digitally built project from the ground up, we'll be able to get those insights continuously and act before maintenance is required. So then we extend the lifetime of the asset and make the project viable.
And that plays into this whole concept of automation. The hydrogen economy never knows where facilities are going to be necessary. It really is dependent on where the wind turbines are built or where you're converting energy from one form to another. Automation, when we talk about that, you're basically talking about the necessity and also the facility of remote automation. Like basically you're somewhere else, your digital technology is somewhere else, and you need a constant link to the facilities you're operating, but you don't need personnel there. for regular checks, as you said. So automation, is that a big word now in the renewable economy?
It is, of course, now, but it also has been in the past because we have an installation, for example, in Norway at Norion, which is an alkaline electrolyzer that runs 24/7, and from Friday afternoon until Monday morning, this facility located in Norway is remote operated from Sweden to be able to limit the need for personnel on site. So these projects are built that way now. Yeah.
So Norway, you mentioned Norway. That's it's been operating since what, 2014?
2014.
Okay, and what does it do?
Water electrolysis for hydrogen production for feeding a chemical site. So a lot of the hydrogen market is not a necessarily new market in terms of we have large sites and facilities that consume hydrogen in its molecular form. And I believe these are some of the first starting points because they already know how much hydrogen they'll need. They have the processes in place. They don't need to adapt that much. We're just going to switch from fossil to renewable hydrogen. And these are some of the quick wins in terms of carbon abatement, so something we should focus on. And then we move down the pecking order in terms of hydrogen for new applications, hydrogen for heating, hydrogen for mobility. These are up-and-coming applications that we also serve, we also work with. But especially in the chemical sector, there's such a known demand for hydrogen, and the way we're going to decarbonize fastest is to switch some of this fossil hydrogen to renewable hydrogen first.
This is, for those who are approaching this new, the electrolysis industry, when they are being honest, and they virtually always are honest, they say that about 1%, maybe a little bit more now, of the hydrogen consumed in industrial processes is actually green. This is a long-standing relationship between natural gas and hydrogen, and this is changing, of course, through the demand to greenify, to reduce carbon emissions, and also energy dependency, which is a fatal equation here in Germany. This leads to my next question, and it's sort of, it plays into the technologies you offer in order to expand production of green hydrogen. Do we have the capacity to actually slowly phase out non-renewable hydrogen and replace it with renewable hydrogen, which basically relies on the facilities you operate, electrolysis and wind turbines, electrolysis and PVCs?
I think it's actually not that much of an either-or question. I think in order to arrive at the quantities of low carbon and no carbon hydrogen that the industry already requires and will require as we transition faster into that future, we're going to have to do both. We're going to have to retrofit existing steam methane reformers with carbon capture units in order to generate at least high quantities of low carbon hydrogen, and then we're going to have to massively scale up and build up renewable hydrogen production in order to meet anywhere near the demand that we have for molecular hydrogen.
Yeah, it is a monstrous equation, isn't it? It's fascinating. Of course, being a Canadian, I'm fascinated in the fact that you're also involved in a project in Canada. Could you tell us about that?
Yeah, that would be the Bécancour project for Air Liquide. So this is a 20 megawatt PEM electrolyzer installation delivered by Cummins on the electrolyzers. But electrolyzer projects are not only the stack. I mean, there's water pretreatment, there's the electrolyzer, there's gas purification, and then all of those modules which came together to form a project, they need to have a safety and supervisory system which talks to the end user's chemical site. In this case, it's Air Liquide Bécancour chemical consuming the hydrogen. That site runs on Emerson's Delta V control system and needs to have visibility into what's going on at this new part of the factory. And we've layered on top of the PLCs, the black box PLCs that are running the electrolyzers. To complete the whole project, we've layered a safety and supervisory system on that is Emerson's Delta V solution that talks to Air Liquide's site in order to make sure that everything is connected and everything is working well, safely.
You just mentioned there Cummins.
Yeah.
The interesting thing for me, and this is just a side note, 20 years ago when I started here, all of the fuel cell and electrolysis, actually electrolysis was barely represented here. And you had fuel cell engineers with their tiny products looking for a market. It's very interesting to note that hydrogenics, which has been around here for decades, has been acquired by Cummins, which is a Fortune 500 company. We have, and we're grateful for it, Emerson here, which is a large company. That is, the larger players economically have realized that we have to do some consolidation and networking in order to make this move forward. And
it's also due to the timing and the staging of where we are. We've moved away from lab scale to pilot scale projects. We're past the point of pilot scale projects. It's really about scaling up now to be able to deliver commercial quantities at commercially viable scale. So that's why Emerson also sees a lot of good engagements at this fair. Our booth is right over here, and we're happy for you to come over and visit it, have those conversations, and help you scale up.
Well, the scale up is one side of the equation here. We who have been here for 20 years are kind of defensive. We always had this technology available. The manufacturers will say, no, it's gotten better right now. We do know that the big equation is the efficiency of renewable energy. We underbid the kilowatt hour price of what you get from the grid, right? That's an important message to get out there. But how to utilize is another equation here. The other side, because you mentioned, okay, so we've been waiting for the quality of the technology. Here's another waiting factor that we're done with. For those of you from Germany, you all know that the government has approved the construction of wind turbines without this limitation of 1 kilometer away from any residential community. Altmaier, I didn't want to mention any names, but largely this policy has made it impossible for the last virtually decade to expand radically renewable energy. We're facing, and when I say we, Germany is facing its incredible dependency on non-renewable energy that could be turned off at any moment. And on the other hand, we're facing a radical expansion of renewable energy here. And here, for me, the question that I always ask larger companies is, do we have the capacity to expand and absorb this foreseeable expansion in hydrogen production? And when I say hydrogen, electricity cannot be absorbed in this quantity into the grid itself.
Yeah.
It has a different cycle of production. So basically, the energy carrier hydrogen is the equation that allows us to utilize optimally all of this renewable energy. Do we have the capacity to deal with this foreseeable increase in quantity?
I think what you've mentioned is correct in terms of that the grid currently is already at capacity from north to south, from where the renewable energy is produced to where large quantities of industrial energy are needed, from north to south. And so the gas grid does offer a pathway which can carry about 6 times more energy equivalent from north to south Germany than the electricity grid. So doing power to X projects, yes, it can be a solution with gas grid blending and injection, but also making that hydrogen transportable in terms of hydrogen derivatives, whether they're methanol, ammonia, or synthetic aviation fuels. And those are interesting processes, and like Haber-Bosch or Fischer-Tropsch synthesis. These are processes that have been known to us and to the industry also for quite a long time. So we're happy to see a new angle to them, and we've been present in those processes also. So
this is why it's so important to have a gas specialist involved in all of this, right? A company with a portfolio. Yeah. So before I forget, though, let's return briefly to this capital expenditure, plant costs, and the operational expenditure equation. You discussed while we were preparing this talk something called a digital twin. And I've never heard this expression used before, so could you tell us a bit about it?
I'm surprised you haven't.
Okay, it may be common knowledge here, but we're techies here.
Yeah.
Fuel cell.
Yeah. Now, digital twin is a big word. I mean, this is a huge concept. I mean, what are we talking about? A 3D model, a CAD model, it's a dummy digital twin in a way, right? But we can also then add some fundamental physics. We can change a model from a static digital twin to a dynamic digital twin. Once the plant is built, we can feed real-time data from the plant back into a digital twin and actually then drive some predictive models or regressive models on the plant performance that give us ways to increase efficiency on our asset. But yeah, during the project phase, during the CapEx phase, what we can do there is to design this plant up front, including all the elements that are going to go into the plant and the connections that the plant is going to have to its offtake. In order, I mean, it's an effort up front, but it allows us to shorten the project timeline and to be more aware of the project budget, to meet that, to make sure everything is working the way we want it to work. And then during the operational phase, the benefits of having a digital twin is that you can do tweaks in the twin and see what those effects of those tweaks would be before you do it in the real plant. Especially in terms of electrolyzer projects, you always want to have a very high, very consistent water purity, because you would otherwise damage the stack and it would be irreparable damage to the project. And so if you want to do some tests around the water purity system, it would be great to have a way to model that first before you actually do it in your live asset, and that's something that the digital twin enables. At Emerson, we work with our Mimic software, which is a fundamental piece of software that allows us to model and design plants before or during operation.
Great. We've unfortunately run out of time, but the conversation could continue. You can see Emerson's booth right over there. And I'm sure Arthur would be willing to take further questions right after the talk at his booth. I've been talking to Arthur Gosling, who is Director of Strategic Sales and Sustainability at Emerson. Arthur, it's been a pleasure talking to you. I hope to see you back here in this forum next year.
Yeah. Thank you. We're here all week, and we're happy to host you at our booth and have some good conversations.
Thanks.
Thank you.